Hello everybody, my name is Mina and I'm a staff software engineer at ARM. Together with Chuo-Ling Chang from Google Research, today we are going to talk about interacting with your hands from virtual to real-world use cases. I'm going to start with an overview of the hand pose estimation and tracking, and I'll present the challenges developers face when trying to implement this on mobile. And afterwards, Chuo-Ling will present a MediaPipe, an ML solution for cross-platform ML applications, and he will also explain how this can be used for implementing hand tracking and gesture recognition applications on mobile. Let's start with an overview of hand pose estimation and tracking. So why tracking your hands and why gesture recognizing? So you've seen recently there is a lot of new technology, very exciting. There is augmented reality, virtual reality, and a lot of smart devices in general. And these devices require more natural way of interactions. We humans are in the center of it, and it's very important for us to be a simple and intuitive way to interact with these technologies. And people have been trying to close the gap between real and virtual, and one such way which comes to mind right away is using your hands, as we are using them anyway every day. You can also see on some of the pictures here a lot of the advancement people have already done, which is quite exciting, and I hope we see a lot more in future. So what exactly is the problem we are trying to solve? Given an input stream, which could be RGB, with or without depth data alongside, we want to estimate the hand pose, the position and orientation of the hand in space, continuously track it, and recognize a set of predefined gestures. Of course, we want to do this on a small portable device, such as AR glasses, VR headsets, watches, mobiles, and of course it has to run in real time. We want to also be able to enable more advanced interactions. We want to be able to manipulate virtual objects. We don't want to just be able to recognize simple gestures. We want to be able to use advanced user interfaces and interact with the world around us. And to do this, we need to know the exact position and orientation of every part of the hand, every joint and finger we have in our hand. And this is known as articulated hand tracking. So this is what we are going to focus on now. In this presentation, we will assume we are using deep learning approaches, but this is a problem that people have been working on for a very long time, and there are a lot of interesting solutions involving computer vision or more traditional machine learning algorithms. So why is this an interesting problem to work on? Well, you have a lot of wide variety of skin colors, and the shape of the hand varies a lot from person to person. And as you can see, the hand has a lot of degree of freedom, and to be exact, that's 27. And this is already very challenging, but this is not all. We also can appreciate that we are going to use these applications in a wide variety of scenarios, and the background will vary a lot, meaning it will have complex backgrounds, cluttered. Oftentimes, the hand will blend with the environment. It will be hard to distinguish. On top of that, the hand is a very fast-moving object, and it can perform complex interactions, and it's self-occluding. Well, what does it mean, self-occluding? It means that you're not always able to see all parts of the hand, and you have to account for that. So now that we know what we are trying to achieve, and we can appreciate that this is a non-trivial problem, well, what are the subtasks we need to solve in order to achieve our goal? Well, first of all, we have to know where the hand is in the frame. So this is called segmentation, and this output can be in the shape of a bounding box where you have the XY position of the corner and then the width and height, or this could be a mask where every pixel in the frame is marked as hand or non-hand. Apart from that, we also want to continuously track our hands, and this will enable us to perform dynamic gestures. These are gestures that are composed of multiple frames. You can imagine one such gesture will be swipe left to right, which you cannot distinguish from a single frame. On top of that, we have a step which we call model fitting. We need some representation of the hand. And this representation can have different shapes and forms. It could be a mesh, it could be a smooth surface, it could be a 3D geometric model created from simple primitives, or it could be a skeleton model, which is quite common with, for example, 21 joint positions. And why is this useful? Well, on one hand, you can imagine that this model will serve as a constraint to our system. It will define what is a plausible result of a hand, what is basically a good result out of our system. But on the other hand, you can also appreciate that we won't be able to perform advanced interactions with the virtual objects if we don't have the exact positions. We need more accuracy, and this accuracy will be introduced with this model. On top of that, we will at the very end perform some gesture classification or gesture recognition. Out of a predefined set of gestures, which could be static, such as thumbs up, thumbs down, or it could be dynamic, such as the swipe we mentioned before, we want to be able to basically classify them. This classification can be performed on top of the input stream from the camera, from the sensor, or depending on your requirements for the system, you can perform them on the already calculated 21 joint positions. Well, why am I saying this? Because if you're using the input stream, you have a lot more data there for every pixel. If you're using the 21 joints, you basically have a vector 21 by 3, for example, XYZ position, and this will save you a lot of bandwidth and might also simplify your algorithms. So this is something you might want to consider. Implementing your solution might look something like this. Starting with the sensor, which is could be an RGB, or it could be RGB plus depth, for example. Streaming, we firstly want to do a hand localization followed by 3D pose estimation and gesture classification. This could be each individual block can be done with a neural network, or it could be one model end-to-end performing the entire task. In the case when each block is implemented by a neural network, you can also imagine that the errors will propagate. And for example, if the first step, which is your segmentation, fails, the entire system fails. Basically, you don't know where is the hand in the frame, so this will fail the entire system. Something to watch out for. The other thing we have to think about when we are analyzing this pipeline is that in between each stage, each of the stages, you will have pre-processing and post-processing, which is something you have to take care of. And you also will have to synchronize among the individual blocks. Your framework where you're implementing this should allow you to adjust for this, and should also possibly give you the opportunity to experiment with different building blocks. So if you're developing a consumer level solution, which has to work in real world scenes with full diversity of interactions, there are a lot of things that you have to keep in mind, a lot of things to consider. And we'll mention here a few. Starting with, of course, the neural networks, which is the most important. You can either build them yourself or find suitable ones. you can appreciate that this is definitely a difficult task. This is another thing you have to also consider, also in the spirit of the neural networks, is your training and testing data. There are lots of available data sets online, but unfortunately, they have a lot of issues. So you might want to consider creating your own data set. For example, some of the issues are with the size and with the diversity of the data. Another thing is that these data sets are often manually labeled, which introduces errors. According to one study, 20% of the annotations disagree due to the manual labeling. And why is that? Is because, as we mentioned before, you don't always see the full hand. So some parts of the hand are hidden, and when you do manual labeling, you're guessing of where these hidden parts are. So there are some inaccuracies introduced there. Another thing people are doing is they're using synthetic data, which is rendered hands, which will introduce you this accuracy for you. But another thing which you might want to consider is using a soft glove for capturing hand poses, like the one on the picture on the right. So what this soft glove will do for you, this was a very interesting paper presented last year at SIGGRAPH, it's very thin and flexible. It will fit your hand and it will provide you the ground truth data, which you can use later on in your data set. So now that we have thought about the datasets issues, these are the first ones that come to mind. But apart from that, you have to assume that these datasets, they don't necessarily include all the diversity you might want. You might so far have fully implemented your system. The testing data is providing you good accuracy. You're happy with that. Then you give it to your colleague. Your colleague has some jewelry or tattoo or nail polish and everything fails right away. So already the segmentation doesn't perform well. This is one of the things you'll have to consider when you're building your consumer-grade application. The other thing which we very briefly mentioned is the sensor. You might have a depth sensor or RGB sensor, but in either case, it's likely that you'll have some motion blur as the hand is very fast moving. So in case you want to consider adding a depth sensor, then you will have to think about the additional cost that it comes with, both the cost for the hardware, but also the additional bandwidth and the power requirements that come with it. So this is some of the consideration you might have. But even if you have just an RGB sensor, you will have some blurry data, and you'll have to decide what's a good trade-off for you between the frame rate and the accuracy of your system. And as well, you will be experimenting with different building blocks, and you will have to decide what is a good resolution here, as the quality of the input will clearly define the quality of your output. So now that we've done all these considerations, you have to remember that we are talking about a complex pipeline. You will be experimenting a lot. You will be debugging and testing. I will recommend you taking a look at some of the ARM tools, such as ARM-NN and ARM Compute Library, especially when you're trying to optimize your application and also to decide which is the best unit to run on in terms of CPU, GPU, NPU, etc. And you will also have to profile with something like ARM Streamline. We have to remember that we cannot use all of the resources available to us because usually the hand tracking is just like a background application. It's only means to achieve what your actual application will be doing. So it cannot be fully utilizing your units. And Streamline will help you decide how to best perform that. Now that we have appreciated that it's a very challenging task and very interesting to work on, you can definitely see the need for a good framework. One such framework will be presented by Chuo-Ling, and it's called MediaPipe, and this will be definitely a viable solution which you should consider for your system. Thank you.
Hi, I'm Chuo-Ling. I'm a tech lead manager in Google Research. So today I'm here to talk about MediaPipe for hand tracking. MediaPipe Hands is an open source solution from Google that performs hand and finger tracking. So the solution predicts 21 hand landmarks in 3D from a single RGB camera. It also supports multiple hands, and together it also outputs handedness classification to tell a left hand from a right hand. The solution is designed to run in real time in the live camera viewfinder on most modern mobile phones, and powered by the MediaPipe framework. The solution runs cross-platform across Android, iOS, desktop, and servers. It also runs in Python. It also runs on the web locally in the browsers. So how does it work? MediaPipe hence is implemented as a two-stage machine learning pipeline, coordinating between two machine learning models, a palm detection model and a hand landmark estimation model. The heavier palm detection model first takes an input image and predicts an oriented region of interest that encloses the hand. Then a more lightweight hand landmark model takes this region of interest, operates within that, and predicts 3D hand landmarks, the 21 landmarks. And these landmarks can then be further used to derive the next region of interest where the hand landmark model can operate within on the next frame. Therefore, with the pipeline, the heavier palm detection model only needs to be invoked as needed, which means it only needs to be run on the very first frame or whenever the hand disappears from the view or whenever the hand landmark model loses track of the hand. So for most frames, only the very lightweight hand landmark model is run. Therefore, the entire end-to-end pipeline can stay at high throughput. Let's dive in more detail on the machine learning models first. So the first model is palm detection model. We've made a design decision where we want to focus more on palm detection as opposed to the more common hand detection. Because first, palms are more rigid. They don't come with all these articulated fingers. Therefore, the palms are just less deformable. Second, palms are smaller. So even with some self-occlusion or with like interlock hands, you can usually separate different palms using non-max suppression. And finally, palms are also roughly square so that we can use just fewer anchors to cover a smaller range of aspect ratios. Our palm detection model outputs a set of SSD-style anchors together with 7 key points on the palm, as shown on the top right corner in the image here. And these key points are used to derive the enclosing bounding box of the hand. And the architecture of the model is shown as the light blue figure on the slide, and where we adopt this feature pyramid approach such that the anchors are not only predicted on the lowest resolution feature layer, which is 8x8 here, that has the most semantic information. They are also predicted from all these higher layer or layers with higher resolution so that we can handle hands with different scales much better. In addition to that, we also use this focal loss proposed in the RetinaNet paper to address foreground and background imbalance issues, which are often quite occurred in hand image data sets because hands usually show up in images only occupying a very small portion of the image. So summarized in the table here, we can see that by combining the use of a feature pyramid together with focal loss, we can get quite some gain compared to a baseline approach in terms of average precision. So next, let's talk about the hand landmark model. So the model outputs three different set of outputs, sharing the same feature extractor. So in addition to the 21 hand landmark in 3D, it also outputs a probability that indicates the likelihood of a hand being present in the region of interest. And also it outputs a binary classification of handedness that shows if it's a right hand or a left hand. The 3D landmarks are trained from a combination of real-world images and synthetic images. So on the top row on the right here, we are showing some examples of the real-world images we use in the training, annotated manually with ground truth 21 2D hand landmarks. And on the bottom, we are showing some examples of the synthetic training images, where the hands are rendered from a 3D hand rendering model and then superimposed on real-world backgrounds. The ground truth annotation there is simply derived from projection of the 3D rendering model. So as shown in the table below, by adding the synthetic data to the real-world data set, we can achieve further improvement in terms of mean square prediction error. And moreover, the use of synthetic data also unblocks 3D prediction because all these are Z values. They are only available from the synthetic data set. Now let's come back to the two-stage machine learning pipeline. So this pipeline can actually be built very easily with the MediaPipe framework because first, the pipeline can be represented as a MediaPipe graph as shown on the right here. And this graph can be quickly assembled from a collection of reusable and customizable nodes and subgraphs provided with the MediaPipe framework. So let's take a deeper look. So on the right in the graph, you can find a hand detection node in one of the purple boxes. So that node itself is actually a subgraph composed of a image pre-processing node followed by an ML model inference node, which runs the palm detection model, followed by a bunch of post-processing nodes. And similarly, on the top, you can see a hand landmark node colored in purple. And that node internally runs the hand landmark model together with a bunch of pre- and post-processing nodes. So in addition to these two main nodes, this graph also uses several utility nodes provided by the MediaPipe framework. For instance, on the top, you can see a flow limiter node, which can reject some incoming frames if it knows that it decides that there are still too many frames being processed downstream in the graph. There is also a gate node that performs similarly and accept or reject the incoming frame based on the allow or disallow signal. There is also a merge node that combines multiple input streams and generate only one output stream based on the particular policy specified. And in addition to these, there's also a previous loopback node used twice actually in the graph. So this node allows an output or some output generated from the current frame to be looped back and used as input in the next frame. Okay, so without going into details, with all these nodes, you can quickly put together a pipeline as described above, meaning the hand detection node is only invoked as needed, and for most frames, only the hand landmark model is run, so the entire pipeline end-to-end can stay at high throughput. And just to further highlight some of the key features of the framework, synchronization across all these multiple time series data streams is actually handled automatically by the framework, which means, for example, if you want to add some rendering functionality into your pipeline as shown at the bottom of this graph to kind of annotate the 2D landmarks inferred from the machine learning pipeline on top of the video frame for visualization, then the framework actually guarantees that these annotations are always rendered onto the exact frame that was used to produce the landmarks. And another feature is this framework lets you build pipelines with parallel branches easily. And you can even go further to specify, I want this branch to run entirely on GPU while the other branches run on CPU in parallel. And as I discussed earlier, the framework also enables or allows loopbacks so that you can reuse the output of the current frame as the input of the next frame. So hopefully at this point, it's already quite clear that in order to deliver a useful end-to-end machine learning solution, it usually takes more than training and running machine learning models. You'll need to design and implement an efficient pipeline. And the MediaPipe open source framework from Google is the tool for you to do that. Now, let me quickly go over some of the main value propositions of MediaPipe. So first, it enables end-to-end acceleration. More specifically, it comes with built-in fast ML inference and processing, accelerated even on common hardware. For instance, it has a deep integration with Google's TensorFlow Lite inference engine, and that utilizes hardware acceleration on CPU, on GPU, or on edge TPU. To give a data point, for instance, on Samsung S9, with a face mesh model we developed, with GPU acceleration, it runs 2 times faster than on CPU. And similarly, with a hair segmentation model we have, GPU accelerated inference runs 6 times faster than on CPU. Also, because the framework comes with a very modular design, you can simply swap different nodes. That allows you to use an alternative machine learning inference engine if that is your preference. The framework also comes with a bunch of GPU-accelerated pre- and post-processing nodes, enabling an end-to-end accelerated pipeline, for instance, all the way from camera input to render output. The framework also lets you build your solution once and then deploy that anywhere. This means the same solution or pipeline you put together can be easily compiled across Android, iOS, desktop and servers, Python on IoT, or on the web. And you can further serve your solution with APIs in all these different languages provided by MediaPipe. And MediaPipe also utilizes different types of acceleration depending on which platform it runs on. As an example, on the left, I'm showing Google Motion Photos running as native Android app. And on the right, I'm showing the same feature, same solution running inside a Chrome browser on desktop. Now, MediaPipe also comes with many ready-to-use solutions. So in addition to the leftmost one I'm showing, which is hand tracking, as we just discussed, there's also face mesh, which predicts 468 face landmarks in 3D. We also have pose tracking. We also have iris tracking that also comes with depth to iris from a single RGB camera. And there's also hair segmentation, and there are many more. So you can find those on using the URL on the top solutions.mediapipe.dev. And just to highlight, all these solutions shown here run real-time on common mobile devices, in addition to running on other platforms. So all these solutions not only serve as examples for you to learn how to build your own pipeline, your own solution using MediaPipe, they are also ready to use, ready to be customized in your own applications. And this is because MediaPipe is free and open source. It comes with very permissive Apache 2.0 license so that you can start building and distributing your own solutions right away. You can also use and redistribute all these ready-to-use ML solutions, or you can even further customize these solutions. MediaPipe is also field tested extensively in Google's products and research. For instance, on the left, you can see that MediaPipe is powering quite a few machine learning features in Google Lens. MediaPipe is used in many Google research projects. MediaPipe runs in Google Nest, both on device, in the cameras, and on the backend servers. MediaPipe also powers several Google Cloud Vision and video APIs, and then it also enabled the AR makeup ads in YouTube. So here, I'm showing a few more examples of how MediaPipe is used across Google's products and research. So if you want to know more about MediaPipe, please visit us at MediaPipe.dev. And that concludes Mina's and my presentation. Thank you.